Welcome to Linear Algebra class. In today's lesson, we are going to talk about section 1.2, that is matrix multiplication. So what do I mean by matrix multiplication? So we studied this something like, if we have a matrix, and I'm gonna say just one matrix, A11, A12, first row, first column, first row, second column, second row, first column, and second row, second column, and we multiply that with another matrix, B11, B12, B21, B22. What we do is first row, first column becomes the part of the product matrix, first row, first column. So if I were to write this, A11, B11 plus A12, B21. Then the second row, first row, second column. So I'm going to deal with this guy, which is A11, B12 plus A12, B22. Third element. So now we are focusing on this guy and this guy. A21, B11 plus A22, B21. And the last element is, if you were to carry out the same operation, A21, B12 plus A22, B22. So for this matrix multiplication to be valid, if I have a matrix M by N, it should be multiplied by matrix maybe N by M1. So the number of columns and number of rows must be same, and the resultant matrix will have dimension M times M1. In this particular problem, that doesn't matter because M and M1, both of them have the same dimension. Now this is called as the dot product. So or sometimes also called as the inner product. And I want to express this in a concise notation. And so we are trying to find out the resultant, and say I want to find out the resultant, say this guy. So I'm gonna express this as something like C, second row, first column, because this is second row, first column of C, is equal to summation A21, B11 plus A22, B21. And I would like to express this in a concise notation. So I would start with indices I, J. As you can see, this guy is I, this guy is I, this guy is I. So what I'm going to do is I'm going to have an index summation K is equal to 1 to 2. because we are running sum from k is equal to 1 to 2. And I'm going to write this down as a 2k multiplied by b k2. So now basically this is super important. So what I want to do is I want to express this sum, and you will see as the indices are going from 1 to 2. So I made a mistake here. As you can see here, this should be A. First row 2 1. First row 4. So second row, first column. No, this is correct. Second row, first column. So as you can see that I have these indices repeated over here. So k goes from 1. And now if you were to expand this, and I would do this just for one exercise, because this sort of notation sometimes could be a little confusing. So this is A 2, k becomes 1, B, k becomes 1, this actually is 1. And I will explain this in just a second, because this guy is here and this guy is here. And B 1 1 plus A 2 2 D 2 1. So what I'm trying to say here is I want you to look at the pattern 2 1. This guy is here and this guy is here. So many a times we can write the matrix multiplication in a very compact notation. Sometimes if you see the books on linear algebra, machine learning, you will see these huge matrix computations would be expressed in a very shorthand notation. And the notation is simply Cij, sum of k is equal to 1 to n a I k multiplied by d k j. And watch the pattern. I goes here, j goes here, and k is the running index. So please keep in mind, this indicates a matrix multiplication using inner product, where the indices can run from k is equal to 1 to k is equal to 10, 15, 17, 19. This can be used for square matrix multiplication, or it can be used for rectangular matrix multiplication, as long as the rows and column rule, the rule that is shown over here is valid. So this is section 1.2. Now, what we want to do is we want to look at the same multiplication in a slightly different fashion. Now, what we are going to do is we are going to write the product. So A times B as column times rows. So columns of A times rows of B. Now I will take the same example. A first row, first column. A first row, second column. B for second row, first column. B, A second row, first column. A second row, second column. Multiplied by B first row, first column. B first row, second column. B second row, first column. And B second row, second column. Now, when we are going to do the column type multiplication, these are columns and these are rows. So what I'm going to do is I'm going to have, and this may look tedious, but I promise you, it's really not. A11, A21, the first column, first row, B11, B21. Then again, what we'll do is first column and the second row. So first column, A11, A21, B21, B22. And this is all going to be in the big resultant matrix. Usually we don't do multiplication like this when we study undergraduate linear algebra. 2, 2. B11, B12, A12, A22, B21, B22. Now the question is, what is the result of this multiplication? And most importantly, is the result same? So I'm going to rewrite the result here. A11, B11, A11, B11 plus A21, B12. So this is 1, 2. This is 1, 2. So 1, 2. A11, B21 plus A21, B22. So next, plus A22, B12, A12, B21 plus A22, B2. And I would encourage you to compare this with the inner product multiplication that we just did. So in contrast to inner product, this is called as outer product. So, and it may seem tedious, but there is an advantage in doing this when we look at uh, matrices as vector spaces, and we will talk about it in near future. Now, let's take a very simple example of if I have a vector u and if I have a vector v. So vector means a series of numbers. So 2, 2, 1. And say v is equal to 3, 4, 6. Now, geometrically, if you want to think about these two vectors, think about as they could be the location of a point in a three-dimensional space. If you have x, y, and z, and I'm just going to guess here. So you have one point somewhere, maybe here. This is your one vector starting from 0, 0, 0, going to the point 2 units in x direction, 2 units in y direction, and 1 unit in z direction. Same thing you can do with this guy. So 3 units in one direction, and then maybe something like this. So 3 units in x direction, 4 units in y direction, 6 units in z direction. Now what I want to do is I want to take an outer product. So let's identify the number of rows and columns. 1 row, 3 column, 1 row, 3 column. So I cannot take a product of u times v because 1 times 3 multiplied by 1 times 3, these numbers are not the same. So to take a product, I need to transpose the second vector. So it will be u transpose. And when I do the transpose, I have 2, 2, 1 transpose with 3, 4, 6. And now what I'm going to do is, let's see if I were to take an inner product, what would happen. So I'm going to show you what happens in the case of an inner product. This is an inner product. What happens in the case of inner product? So it will become 2 times 3 plus 2 times 4 plus 1 times 6. So what happened is I just got one single number, 6 plus 8 plus 6. So 6 plus 8 plus 6 is equal to 20. Now what I want to do is I want to take an outer product. So if I want to take the outer product, what I need to do is I need to do u transpose v. So check this out. So this becomes 2, 2, 1, 3, 4, 6. And this is slightly different convention in the book because Professor Strang assumes the vectors in column fashion. So this is the convention in the book. So if you want to follow the convention in the book, you can do the same exercise, but just assume vectors to be like this. So this is for the book. Now here, it's gonna look like 3 times 2, 2, 1 plus 4 times 2, 2, 1 plus 6 times 2, 2, 1. Now I want to give you an important observation. So note, this guy is same. And what is happening is the column, first column of the resultant matrix is scaled by 3. Second column of the resultant matrix is scaled by 4. And the third column of the matrix is scaled by 6. So this is nothing but same vector scaled multiple times. So this is 6, 6, 3, 8, 8, 4, 12, 12, 1. Now, if you look at what we talked about independence of vector, these 3 columns are not independent. So each column is dependent on previous column, and there is a ratio. That ratio could be different, but there is a ratio. So what it means is there is only one independent column. And from the theorem, which means one independent row. What that means is the rank of this matrix. Rank is defined as number of independent rows or columns of this matrix is 1. This is a very important observation. Now, this will be used in further calculations. And the important observation I will just note down. So the rank of the matrix, which means number of independent columns, is equal to column rank or row rank and this is the number of independent columns or rows that are inside the matrix. We just talked about the column row multiplication of the matrices. Now, what does this mathematical jugglery give us? So what is the advantage of doing something like this? So when you look at the application of linear algebra, of linear algebra, and I'm talking about the, the fields like robotics, data science, or machine learning. The idea is at the end of the day, or for that matter, CFD, or maybe the other fields are computational modeling. So I'm going to say computational modeling. So at the end of the day, what we have is we have a very large system, very or finite element analysis, FEA, or boundary element analysis. Or CAD, or CAM. So very important problem that we are trying to solve is we have a system of equations AX is equal to B. The idea is somehow we will form this They could be compatibility equations. They could be constraint equation. That could be a Navier-Stokes equation. That could be Maxwell's equation. So we are going to get this very large, sometimes with lots and lots of zeros, with lots of zeros, with lots of zeros. And we may have to obtain this. So we need to get this, find. And this resultant is could be forces, moments, uh, the velocities, accelerations of the robot, or in machine learning, the weights of the neural network. And sometimes you have this as known. These are the external loads or the information that is coming from the previous neurons. And the idea is, how do we obtain this? How do we solve this system? Solving quickly and correctly and accurately using computer. And that is where the numerical linear algebra comes into place, or computational linear algebra comes into place. So the classic problem, what I want to define this as something similar to, if you think about what we want to do is, we have a vector, and for generalization, I'm going to call this a matrix that needs to be composed into its two fundamental parts. One part is A and other part is X. So if I want to replace the nomenclature, just like the way discussed in the book, the problem is something like this. We want to factor, and this is a very common problem, factor matrix A. This could be square or rectangular into a matrix C and R, so that we can study C, K, R, K. So these are the elements. So we have this matrix that needs to be factored into its subcomponent. Think about it, trying to resolve the forces or trying to find out the subcomponents they make that whole matrix. And this factorization is super duper fundamental. So factorization is a very fundamental operation in linear algebra, especially when you want to apply linear algebra to all these different fields. So let me discuss the most important factorization, and we'll spend some amount of time studying these factorizations. And clearly, you can use any system like MATLAB or Julia to do these factorizations. So we will not look into the code, but we will have homework exercises where you can apply those codes. So first factorization is A is equal to lower triangular and upper triangular matrices. So L is the lower triangular, U is the upper triangular, and when you multiply these two, L and U, these two matrices, you go back to A. And what do I mean by lower triangular and upper triangular? So if you look at the triangle, so there is, these are the two matrices, L and U, and this is the lower triangular and this is the upper triangle. And when you perform the multiplications, so basically you get the resultant matrix. The next factorization is something called as A is equal to Q times R. And this is again a matrix. However, something that important to note, that matrix Q is an has orthonormal columns. And R is upper triangular. So what it means is, if you were to decompose this, and if you were to do Q transpose Q, so if you transpose the matrix, multiply the same matrix, you will land up with an identity. And this is called as orthogonalization. And again, why do we need to do the orthogonalization? Because in certain cases, when we are trying to solve huge number of equations, this special structure of the matrices allows us to skip some steps and go to the solution very, very quickly. And it may not be evident when you are trying to solve maybe a system of equation that is 10 by 10, 15 by 15, 20 by 20. But I want you to think about a million by million, or 3 million by 3 million. And you have to solve those equations in every time step, say half a second or in milliseconds. So all that computation machinery will be super duper useful. Next is, consider this matrix S, and we want to split this matrix into 3 matrices, where, as you know, that Q is an orthonormal matrix. Lambda is, they are the nothing but the eigenvalues of S. And I need to mention S is a super important matrix which is symmetric. So S is equal to S transpose. And this type of matrix you will see in lots and lots of applications. So you will, when we derive the equations for mechanical systems, electrical systems, coupled system, robots, essentially robots are coupled system, mechanical to electrical, so mechatronic system interfacing with another mechatronic system, or humans. So that is what this comes to. And these are orthonormal matrix of eigenvectors. So you have orthonormal matrix of eigenvectors. They form the columns of Q. And this is a symmetric matrix. So please note, this is symmetric matrix, but this is not a positive definite matrix. So I need to say S is a symmetric matrix, but not, or could be. It could be, or maybe, or may positive definite. So when you say if the matrix is positive definite, you are going to add one more condition onto S. If you want S to be positive definite, then all lambdas, they have to be positive. So that is additional condition. But here we are not specifying that. The next thing is A is equal to X lambda X inverse. This is the diagonalization. With independent eigenvectors. So what do I mean by diagonalization with independent eigenvectors? So think about the eigenvalue problem that we briefly talked in the last class. So the problem was AX is equal to lambda times X. So basically we talked about this diagonalization problem, and this could be written as lambda X, but since this is a diagonal matrix, you can change the order. So X lambda equal to AX. You multiply left and right side by X inverse. So multiply by X inverse. So this becomes A X lambda X inverse. So this is the diagonalization problem. And this is only possible, so which is very important, if it has independent eigenvectors. So if your matrix has, it's a 3 by 3 matrix, needs to have rank is equal to 3, only then this diagonalization is possible. So you should have 3 independent eigenvectors. So 3 independent eigenvectors. And the fifth and perhaps very commonly used decomposition is singular value decomposition. Now, as you can see, the eigenvectors, eigenvalues, that analysis, and for that matter, inverse, is only applicable to square matrices. But many a times, the matrices that we see in data science, many a times we see matrices in robotics, machine learning, they are not square. They could be rectangular. And rectangular means it could be m times n, where m is not equal to n. So what happens in that case is you have u and v. U and v are orthonormal. Normal. Singular. Vectors. So this is super important. They will be orthonormal singular vectors. And think about it like similar to eigenvalue decomposition, but now the matrix is not square. Now, if you think about what are the advantages and disadvantages, usually there are different techniques in numerical linear algebra that rely on certain type of decomposition. And this certain decomposition is part of many of the algorithms that are used in implementing inside the computer code or in MATLAB. So this is where we are going to stop today.